So we're going to play this game a couple more times, just looking at different charged objects and trying to calculate expressions for the electric field due to those charge distributions. So the thin rod is one that shows up quite a bit. It's kind of a common and simple example of a charge distribution. Another one that's useful, not so much in its own right, but more for developing other things we'll talk about later, is a uniformly charged thin ring. Okay, so let's say you have, and I'm going to draw my coordinate axes a little bit in perspective here, where x is kind of like that and z is kind of like that. And what I'm going to draw is a thin ring that lies in the xy plane. In fact, I'll kind of draw the axis going in front like that. Okay, so the z-axis is coming through the center of the ring, and it's perpendicular to the ring, and the ring is in the xy plane. And really, this is the positive x direction, and this is the negative x direction. So draw it like that. Okay. So this ring has a radius. We'll call it r. It has a total charge q. And our job is to find the electric field at an observation location that is right on the z-axis, going through the center of the ring. So we'll just call that distance z. Okay? So this is observation location 0, 0, z. So we're going to go through the same steps again. We're going to break it up into pieces, write an expression for the delta E of one piece, sum up all the delta E's, and then check the result. Before we even do the calculation, what would you expect if this is a positively charged ring, for example? When we get a result, what would you expect for the direction of the net electric field due to that positively charged ring? Down the z-axis, right? Down the z-axis. Why? What's happening? When you break, okay, so let's break it up into pieces. Here's a piece that's, say, at some random location in the xy plane. I would have to look at an r vector that points from the source to the observation location, kind of like that. And then the delta E would point away from that positively charged piece. And so we have something that has, it has a z component, it has an x component, and a y component. But what's going to happen to all the x and y components when we add everything up? They're all going to cancel out. They're all going to cancel out, right? And again, we can use the computer to visualize that for us. So let's take a look at this one, I believe. So here's our ring, and it's on, again, the xy plane. So let me change the perspective a little bit. So we're going to break it up into pieces. Okay, so there's this first piece is right at the top here, this little chunk, this little cyan globe, if you can see this. Let me kill the lights, that might help. So we break it up into point charges. There's a little point charge at the top, a little chunk of this ring. We draw the r vector. The green arrow is the r vector that points from the delta Q to the observation location. And then the orange arrow is the delta E, the electric field just due to that piece alone, right? Go to the next piece, and now we're just going to keep all the delta E's on the screen here. So we go to the next point along the ring, calculate that delta E, calculate the next delta E due to the next piece, and so on, and so on, and so on, going around the ring. if I rotate this back to look like this as we go around the ring, we see that we get a bunch of delta E's that are all the same magnitude, right? All kind of pointing radially outward, but yet they all have a net positive Z component. So all the X and Y components, if we look at it from this perspective, will cancel out, but all the Z components will add together, and so we end up with a rather large electric field drawn to this scale, right? We had to draw the scale so we could see the delta E's, and so the E is kind of big. Okay, so we get the result we expect. Okay, we get the result we expect. So let's actually try it. Let's actually try going through, or at least setting up the integral, the analytic integral, to actually get a result here. Okay, so we've divided up the delta Q's. We say that we want to break this up into little point charges, each with a charge of delta Q. Okay, and then we're going to write an expression for the electric field of one piece. Well, the electric field is going to be 1 over 4 pi epsilon 0 delta Q over little r squared times r hat. So I have to figure out what this r is. Tell you what, let's do it this way. Changing the rules slightly, but just to make it a little simpler to see and not have to deal with so much math, I'm going to look just at this piece at the very top. Okay. So here's the r vector. Points from the very top down to here, and it's making a delta E in that direction. What is the position, the vector position of a piece at the very top? That would be x equal to 0, y equal to capital R, right, the radius, and z equal to 0, right? And then our observation location is 0, 0, z. So little r is going to be 0, 0, z minus 0, r, 0, or 0, negative r, z. The magnitude of that thing is going to be square root of r squared plus z squared. Okay? And then r hat is 0, negative r, z over square root r squared plus z squared. Okay? So, I write all this out as 1 over 4 pi epsilon 0 delta Q over square of this thing is the square of this thing, so that's just r squared plus z squared times the vector 0, negative r, z over square root r squared plus z squared. If I simplify that a little bit, I'm going to have this factor to the 3/2 in the denominator times this vector 0, negative r, z. Okay? Are we okay so far? So then we already said that only the z component matters because all the x's and y components are going to cancel out. Okay? So I'm just going to worry about the z component. And the z component of this thing, delta E sub z, is 1 over 4 pi epsilon 0 z times delta Q over r squared plus z squared to the 3/2 power. And I'm almost ready now to do the summation, but there's one thing I got to do. Anybody remember from last time what we have to do? What do we have to do to that delta Q? Okay, it has to turn to dq. That's true. Everything has to become an infinitesimal, but we have to write this delta Q in terms of, what do we call that special thing? The variable that's changing as we go around the ring is called, in general, it's called the integration variable, right? So we have to put delta Q in terms of the integration variable. The integration variable is the variable that's changing as we do the summation, okay? So what's changing as we move from one piece to the next as we go around this ring? The angle, yeah, the angle is changing, right? We can describe where this particular piece is by looking at the angle theta. By looking at the angle theta, okay? So let's ask this question. And we'll see how we do here. But we have a uniformly charged ring Q, radius r. We want to find delta Q. What is delta Q expressed in terms of the given constants and an integration variable? There's several different choices to choose from. You can try working it out, or you can just kind of go through each one in turn and see which one makes the most sense. But talk it over with your neighbor. See which one works the best. If you think about breaking this into the number of segments, remember that Q, the total Q, is N times delta Q. That may help. N is the number of little pieces. All right, we have a large vote for 3. We have a smaller vote for 4, and some people are saying 2. Well, 2's out because the integration variable doesn't show up, right? I mean, we don't have any theta in there at all, so we have to have something in terms of a delta theta. 1's out because it's in the denominator. So let's look at 3, 4, and 5. 3 looks like it should work, but not quite, because if you actually look carefully, the units don't work out. The units of delta Q should be just coulombs, right? So we have Q, which is in coulombs, times theta, which is in radians, which really isn't a unit, divided by 2 pi r, which is in meters. So 3 gives you coulombs per meter, and that doesn't work. So it looks like, in terms of the units, 4 would work because we have theta, which is unitless, divided by 2 pi, or Q times r divided by 2 pi r. In fact, 4 and 5 are identical, which is just a factor of r multiplied top and bottom. And so either 4 or 5 is the correct result here. So how do you actually get this? If the length has to be equal to n times delta L, right? What's the total length of the circle? 2 pi r. How do I place a delta L, meaning a little slice of circumference, a little arc length, in terms of theta? See how many people remember what the definition of a radian is. So in other words, I want to put this in terms of delta theta, a little slice of angle. How does the length relate to the little slice of angle? How do we define that angle? Delta theta is equal to delta L over, not 2 pi, over, well, not delta r, but just the radius r. That's what a radian is. It's that little length divided by the radius, okay? So delta L would be r times delta theta. Plug that in, and you get 2 pi r is equal to n times r times delta theta, but it's also q is equal to n times delta q. So I take the ratio here, I get delta q over r delta theta is equal to 2 pi r, or, q over 2 pi r. Q over 2 pi r. Radius cancels out on both sides, and so we can say delta q is equal to q over 2 pi times delta theta, okay? All right, real quick, let's plug this all in and see what we get. we have delta E sub z is equal to 1 over 4 pi epsilon 0 z times q over 2 pi times delta theta, just making that substitution, over r squared plus z squared to the 3 halves. Okay? We want to sum this up. We want to turn this into infinitesimals and do an integral. An integral from where to where? From what? 0 to 2 pi, right? We're summing up over the entire circle. So 0 to 2 pi radians. Well, let's look at this expression. The only thing that's changing is theta. Is z a constant? Yeah, that comes out. Is q constant? Yep. Is 2 pi a constant? Yeah, obviously. Is r a constant? Yeah, the radius isn't changing. Is z a constant? Yeah, everything in here is a constant. So this all comes out of the integral. And so this becomes z times q over 2 pi over r squared plus z squared to the 3 halves. Integral from 0 to 2 pi of d theta. And if I do that integral, what do I just get? 2 pi. 2 pi. So the 2 pi cancels out. And we get, for our result, the electric field of a uniformly charged ring is equal to 1 over 4 pi epsilon 0 q times z over the square root of r squared plus z squared to the 3 halves. Okay? Real quick, how can we check it? Where do you know a result? What's the electric field have to be at the center? Why? Yeah, all the fields would cancel out, right? They all be pointing in opposite directions. If I plug in z equals 0 into this expression, what do I get? I get 0. Okay, so it seems to work. Okay, we'll pick up with this next time, and we'll use this to derive some other results.